apply torque to remove a tooth.
You get a giant crowbar.
Have you tried the door slamming to remove a tooth before?
No,
Maybe when I was a kid.
I just,
I don't remember whether we did anything like that or not. I had numerous ways which they came out, but I don't know if we ever did the door thing or not.
I remember trying the door thing and was not successful.
well, it's hard,
It hurt a lot.
it's hard to get a good grip on it, you gotta get a knot on it.
I remember one came out in an Apple, that worked really well.
So that's one thing that Dad was really squeamish about is loose teeth. If some kid came up, he was the head of the school, so if a kid came up and started wiggling a tooth, he would have done it.
Are we still on AC circuits?
Yeah, we are. I left this up because I wanted to remind myself that I'm not giving you that formula on the test.
Well, that was very helpful, thank you. So we have to derive it ourselves in the test?
Yeah.
At least we know there's likely a point where we'll be using that on the test, since he's saying that.
All right, so the last thing we did with AC circuits,
I don't
Gonna
know if
jump
we're
ahead.
able to tell anything.
so we got as far as, do we do an RC circuit in there? Can't quite tell what
Yeah,
you did.
ACRC series circuit, capacitor, resistors, inductors, phasers,
All right,
normal American power, RMS value.
have we done the phaser, the inductor phaser?
I only had the one phaser with the,
Let's see. And then your notes.
my notes are a little bit different styles.
You got as far as impedance with that circuit,
And, okay, we did do inductor there. All right. So let's take a look. At RLC circuit. So it's an AC RLC series circuit.
Yeah.
And it's very similar to the one we did, except for the fact that we have an inductor in there now. So let's set up the phasor diagram. And is there anything that's going to be the same for all four components? When I say the same, basically is voltage or current common to everything?
Current.
Yeah. So I'm going to start out with my current phasor. And since it is the same for everything, my current phasor is the same as that for the capacitor, same as for the inductor, same as for the resistor, same as for the power supply. That's four of the phasors right there. There'll be two phasors per component, one for current, one for voltage. And that's half. Voltage phasor for the resistor. Now we get into the phase rules. I know that the voltage for the resistor is in phase with current for the resistor. Let's see, Iceman, I know the current for the capacitor leads voltage for the capacitor by pi over 2. And current for the inductor, well, actually it's VI. Voltage for the inductor leads current for the inductor by pi over 2. So I know where the current phasors are, so I can, voltage for the resistor is right along line of it. The inductor, I know that the voltage leads the current, so for the inductor, it's gonna be, that should be a right angle there. And for the capacitor, the voltage lags. That's also 90 degrees. Now, I didn't give enough information to know if VL or VC is longer. For what we're doing right now, not particularly crucial. Let's just, for the, well, actually for today, let's stick some numbers in there. Let's figure out which one's supposed to be longer. That one is 15 ohms. The inductor is 45 millihenries. And for the capacitor, we will set 200 microfarads. Let's assume that we have an RMS value of 120 volts and a frequency of 60 hertz. So from this, we can figure out whether VL or VC is longer in this particular case. Because we have another set of rules here. I know that the capacitive reactance is 1 equals 1 over omega C. And the inductive reactance is equal to omega L. So we need to figure out omega. What is omega? Given the information written on the board, how do we find omega?
Something with the frequency.
What is omega? Well, why don't we start there?
2 pi the frequency.
Okay, answering the first question, what is omega? Answering.
Angular frequency.
Yeah, and it is indeed 2 pi times the frequency.
We all got it, yeah.
So that's 2 pi times 60 hertz, which is 169.7056. No, that's not right. It's 300 something. 376.99. I'm going off memory here, which is never a good thing.
That's correct.
All right. What would units be?
Radians per second?
Yes. So I know omega, so now plugging in over there, we have x sub c is 1 over 376.99 times, I guess that would be radians per second, times my capacitance, which is 200 times 10 to the negative 6 farads. And it looks like, Paul, we are counting on you. Unless someone else wants to pull out a calculator. Oh, there we go. David's got a calculator too. Be nice for confirmations.
13.2629.
13.2629
Yes.
units.
Seconds over Fahrenheit, which are just the
Farads.
No, it's not just Fahrenheit. Is it just Fahrenheit?
That is farads.
Okay, it's just Fahrenheit.
We going for Fahrenheit?
I don't know.
It sounded like you combined several different words into one, so. So seconds per farad, but we've got a shorthand. There is a 1-word unit for this.
The Henry?
No,
Henry?
sorry, Henry and Internet don't show up yet. Yes, it is something. All right, so why don't we bring up another set of rules that we know. I know that the amplitude of the voltage for the resistor is equal to the amplitude of the current for the resistor times the resistance. I know the voltage for the capacitor, amplitude is equal to the amplitude for the current across the capacitor times the capacitive reactance. And VL is equal to IL.
Ohms.
I think that was the word ohm,
Yeah.
as opposed to O. So 13.2629 ohms. All right, X of L is equal to omega L, so 376.99 radians per second times 45 times 10 to the negative third henries. Let's see, we've now calculated omega 8.761. X is C 13.229.
.5080. Oh, 45. I put 4.
That would definitely change the answer.
16.9646.
Would you get it again?
16.9646
Units?
ohms.
Yeah. Or henries per second,
Henries per second.
or radians per second units.
That's an H is in Henry.
Say it again?
That's the H is for Henry, right?
Yes.
Okay.
So 16. What I wanted. .9646. I know that VL is the current times XL, and VC is the current times XC. Since the currents are the same, whether VC or VL is bigger depends upon the reactance. And since the inductive reactance is bigger than the capacitive reactance, I know VL is going to be bigger than VC. Now, if you're just sketching the phase diagram, it's not that crucial. But just for the sake of some accuracy, let's go ahead and make that one shorter than VL. I need to figure out what the voltage of the power supply is, because I should have 8 phasors, and voltage of the power supply is the one I'm missing. So I need to add these 3 phasors, and you add them like vectors. First thing I'm going to do, add the ones that are anti-parallel. So since that one's bigger than this, that's going to be VL minus VC. And now I add that sum to this. That's supposed to be straight. And that, because I know that the voltage of the power supply, if I'm going from here to here, if I go the direct path, that's the voltage of the power supply, or I could go around the others, and that would be the voltage of the sum of the other components. So that's why adding them gets me the voltage of the power supply. And now I've got the Pythagorean theorem. I know epsilon squared is equal to VR squared plus VL minus VC squared. figure out, so I guess it's not necessarily ultimately, but right now I want to figure out what is the impedance of the circuit. Oh, I guess that's the other one. Squared equals IR squared plus I x sub L minus I x sub C squared. I can factor I squared out or divide everything by I squared, and so I end up with Z squared is equal to R squared plus XL minus XC squared. And so my impedance of the circuit is the square root of R squared plus XL minus XC squared. Now, if you had speculated that you hadn't gone through to calculate XC and XL, and so I've got my two phasors, VL and VC, and if you said VC is longer, then this would have been ultimately XC minus XL, but it's squared, so it doesn't really matter. Let's go ahead and figure out the impedance. We got numbers here. So in this particular case, our impedance is 15 squared, square root of 15 squared plus 16.9646 minus 13.2629 squared. And looking at these numbers enough, I think it's 15.4500.
Close, yeah. 14.4464.
14.
I'm sorry, 15.4464.
15.4434.
64.
4464. Units.
Ohms.
Yeah. Questions before I erase the stuff on the right hand side?
That's the easy stuff.
That's the easy stuff?
Yeah. Why didn't we do inductors with DC circuits?
You asked that last time.
Did I? I still don't know why. Where somebody's seeing them now.
Well, we did one. I was thinking we did one, when we had we powered up a capacitor with a DC power supply, and then we disconnected the power supply. So we had a CL circuit.
What do they do again? We have resistors that kind of slow the flow of electricity, capacitors store electricity. What do inductors do?
Sit there and look pretty. The main thing that it does is it prevents rapid change. So that if the current ramps up quickly, that the inductor is going to try to slow that down, or if it slows down, or if it drops off quickly, it's going to try to slow the drop off.
Isn't that what a resistor does?
Resistor is going to slow it, slows everything down. Inductor, resistor is going to prevent the maximum, basically limit what the maximum current is. What the inductor is limits how quickly it gets there.
Oh, okay.
Read recently another way of looking at it, and this didn't really help me, but I'll throw it out there in case it helps you, that a capacitor stores energy in an electric field, and an inductor stores energy in a magnetic field. If it works for you, great.
I suppose maybe that's why we weren't talking about inductors as much before too, because we're talking about magnets now.
Yep, that probably another good reason. I want to know is when time is 0.01 seconds. I would like to know the current, the instantaneous current, and the voltage across all four components. So to do that, we need equations. I have a generic equation here for the instantaneous value. So generically, I is equal to whatever the amplitude is times the cosine of omega t plus 5. I do need to set out one other thing. Let's make the phase shift for the power supply to be pi over 6.52 something.
Another one that I've written down enough times, I should know by now. 523599. I don't need to put units since we're talking about radians, but if you wish, that's radians. So what we're going to do is I'm just going to, I know that this right here is pi over 6. If this is my initial, if this is a time is equal to 0, that would be pi over 6. Well, I can figure that angle out right there, and so then I can figure out what the phase shift for VR and all the currents are. So let's figure out this one right here that I'm going to label as theta 1. I need to give it some name, and I don't want to use phi. Remember that I'm just adding, using Pythagorean theorem here. So I know that theta is the arctangent of opposite over the adjacent, that's VL minus VC, over